In digital computer programming, a bitewise operation operates on one or more bit patterns or binary numerals at the level of their individual bits. It is a fast, primitive action directly supported by the processor, and is used to manipulate values for comparisons and calculations. On simple low-cost processors, typically, bitewise operations are substantially faster than division, several times faster than multiplication, and sometimes significantly faster than addition. While modern processors usually perform addition and multiplication just as fast as bitewise operations due to their longer instruction pipelines and other architectural design choices, bitewise operations do commonly use less power because of the reduced use of resources. Bitewise operators, in the explanations below, any indication of a bit's position is counted from the right side, advancing left. For example, the binary value 0001 has zeros at every position but the first one. Not, the bitewise not, or complement, is a unary operation that performs logical negation on each bit, forming the ones complement of the given binary value. Bits that are 0 become 1, and those that are 1 become 0. For example, not 0111 equals 1000. The bitewise complement is equal to the 2's complement of the value minus 1. If 2's complement arithmetic is used, then, not x equals AXA1. For unsigned integers, the bitewise complement of a number is the mirror reflection of the number across the halfway point of the unsigned integers range. For example, for 8-bit unsigned integers, not x equals 255, x, which can be visualized on a graph as a downward line that effectively flips an increasing range from 0 to 255, to a decreasing range from 255 to 0. A simple but illustrative example use is to invert a grayscale image where each pixel is stored as an unsigned integer. And, a bitewise and takes two binary representations of equal length and performs the logical and operation on each pair of corresponding bits. The result in each position is 1 if the first bit is 1 and the second bit is 1. Otherwise, the result is 0. In this, we perform the multiplication of two bits. That is, 1 0 equals 0 and 1 1 equals 1. For example, 0101 and 0011 equals 0001. The operation may be used to determine whether a particular bit is set or clear. For example, given a bit pattern 0011, to determine whether the second bit is set we use a bitewise and with a bit pattern containing 1 only in the second bit. 0011 and 0010 equals 0010. Because the result 0010 is non-zero, we know the second bit in the original pattern was set. This is often called bit masking. If we store the result, this may be used to clear selected bits in a register. Given the example 0110, the second bit may be cleared by using a bitewise and with the pattern that has a 0 only in the second bit. 0110 and 1101 equals 0100. Because of this property, it becomes easy to check the parity of a binary number by checking the value of the lowest valued bit. Using the example above, 0110 and 0001 equals 0000. Therefore 6 is divisible by 2 and is even. Or, a bitewise OR takes 2-bit patterns of equal length and performs the logical inclusive OR operation on each pair of corresponding bits. The result in each position is 1 if the first bit is 1 or the second bit is 1 or both bits are 1. Otherwise, the result is 0. For example, 0101, Oregon, 0011, equals 0111. The bitewise OR may be used to set selected bits, such as a specific bit in a register where each bit represents an individual Boolean state. For example 0010 can be considered a set of 4 flags, where the first, third, and fourth flags are clear and the second flag is set. The fourth flag may be set by performing a bitewise OR between this value and a bit pattern with only the fourth bit set. 0010, Oregon, 1000, equals 1010. This technique is an efficient way to store a number of Boolean values using as little memory as possible. XOR, a bitewise XOR takes 2-bit patterns of equal length and performs the logical exclusive OR operation on each pair of corresponding bits. The result in each position is 1 if only the first bit is 1 or only the second bit is 1, but will be 0 if both are 0 or both are 1. In this we perform the comparison of two bits, being 1 if the two bits are different, and 0 if they are the same. For example, 0101, XOR 0011, equals 0110. The Byte Wise Xor may be used to invert selected bits in a register. Any bit may be toggled by XORing it with 1. For example, given the bit pattern 0010, the second and fourth bits may be toggled by a Byte Wise Xor with a bit pattern containing 1 in the second and fourth positions. 0010, XOR 1010, equals 1000. This technique may be used to manipulate bit patterns representing sets of Boolean states. Assembly language programmers sometimes use XOR as a shortcut to setting the value of a register to 0. Performing XOR on a value against itself always yields 0, and on many architectures this operation requires fewer clock cycles and/or memory than loading a 0 value and saving it to the register. Mathematical equivalence, assuming x, y, for the non-negative integers, the bitewise operations can be written as follows. Where is the number of bits in for all? Atomic inputs, for the examples above often 3 and 5 are used as inputs. They correspond to the unchanged statements among the two are logical connectives. For the 3 are case 15, 51 and 85 would be used. These numbers are found in the number triangle Euro-She 211344. 101, 3500110101, 1551 85 000111110011010010101. Bit shifts. The bit shifts are sometimes considered bitewise operations, because they treat a value as a series of bits rather than as a numerical quantity. In these operations the digits are moved, or shifted, to the left or right. Registers in a computer processor have a fixed width, so some bits will be shifted out of the register at one end, while the same number of bits are shifted in from the other end. The differences between bit shift operators lie in how they determine the values of the shifted-in bits. Arithmetic shift. In an arithmetic shift, the bits that are shifted out of either end are discarded. In a left arithmetic shift, zeros are shifted in on the right. In a right arithmetic shift, the sign bit is shifted in on the left, thus preserving the sign of the operand. This example uses an 8-bit register. 00101111 left shift, equals 00101110. 10,010,111 right shift, equals 11,001,011. In the first case, the leftmost digit was shifted past the end of the register, and a new 0 was shifted into the rightmost position. In the second case, the rightmost one was shifted out, and a new one was copied into the leftmost position, preserving the sign of the number. Multiple shifts are sometimes shortened to a single shift by some number of digits. For example, 00101111 left shift by 2, equals 01011100. A left arithmetic shift by n is equivalent to multiplying by 2n, while a right arithmetic shift by n of a 2's complement value is equivalent to dividing by 2n and rounding toward negative infinity. If the binary number is treated as 1's complement, then the same right shift operation results in division by 2n and rounding toward 0. Logical shift. In a logical shift, zeros are shifted in to replace the discarded bits. Therefore the logical and arithmetic left shifts are exactly the same. However, as the logical right shift inserts value 0 bits into the most significant bit, instead of copying the sign bit, it is ideal for unsigned binary numbers, while the arithmetic right shift is ideal for signed 2's complement binary numbers. Rotate no carry. Another form of shift is the circular shift or bit rotation. In this operation, the bits are rotated as if the left and right ends of the register were joined. The value that is shifted in on the right during a left shift is whatever value was shifted out on the left, and vice versa. This operation is useful if it is necessary to retain all the existing bits, and is frequently used in digital cryptography. Rotate through carry. Rotate through carry is similar to the rotate no carry operation, but the two ends of the register are separated by the carry flag. The bit that is shifted in is the old value of the carry flag, and the bit that is shifted out becomes the new value of the carry flag. A single rotate-through carry can simulate a logical or arithmetic shift of one position by setting up the carry flag beforehand. For example, if the carry flag contains 0, then X right rotate-through carry by 1 is a logical right shift, and if the carry flag contains a copy of the sign bit, then X right rotate-through carry by 1 is an arithmetic right shift. For this reason, some microcontrollers such as low-end PICs just have rotate and rotate-through carry, and don't bother with arithmetic or logical shift instructions. Rotate-through carry is especially useful when performing shifts on numbers larger than the processor's native word size, because if a large number is stored in two registers, the bit that is shifted off the end of the first register must come in at the other end of the second. With rotate-through carry, that bit is saved in the carry flag during the first shift, ready to shift in during the second shift without any extra preparation. Shifts in C, C++, C, Python, in C-inspired languages, the left and right shift operators are, and, respectively. The number of places to shift is given as the second argument of the shift operators. For example, assigns X the result of shifting Y to the left by 2 bits. In C, the result of right shifting a negative value is implementation defined, and the result of left shifting a signed value is undefined if the result cannot be represented in the result type. In C, the right shift is an arithmetic shift when the first operand is an int or long. If the first operand is of type uint or long, the right shift is a logical shift. There are also compiler-specific intrinsics implementing circular shifts, like ROTL8, ROTL16, ROT8, ROT16 in Microsoft Visual C++. Shifts in Java. In Java, all integer types are signed, and operators perform arithmetic shifts. Java adds the operator to perform logical right shifts, but because the logical and arithmetic left shift operations are identical, there is no operator in Java. More details of Java's shift operators, the operators, and are called the shift operators. The type of the shift expression is the promoted type of the left-hand operand. For example, a byte 2 is equivalent to a byte 2. If the promoted type of the left-hand operand is int, only the 5 lowest order bits of the right-hand operand are used as the shift distance. It is as if the right-hand operand was subjected to a byte-wise logical AND operator and with the mask value 0x1f. The shift distance actually used is therefore always in the range 0 to 31, inclusive. If the promoted type of the left-hand operand is long, then only the 6 lowest order bits of the right-hand operand are used as the shift distance. It is as if the right-hand operand was subjected to a byte-wise logical AND operator and with the mask value 0x3f. The shift distance actually used is therefore always in the range 0 to 63, inclusive. The value of ns is n right-shifted s-bit positions with 0 extension. In bit and shift operations, the type byte is implicitly converted to int. If the byte value is negative, the highest bit is 1, then 1s are used to fill up the extra bytes in the int. So byte b1 equals -5. Int I equals b10 x0200 will give I-5 as result. Shifts in Pascal. In Pascal, as well as in all its dialects, the left and right shift operators are SHL and SHR, respectively. The number of places to shift is given as the second argument. For example, the following assigns X the result of shifting Y to the left by 2 bits. Applications. Byte-wise operations are necessary particularly in lower-level programming such as writing device drivers, low-level graphics, communications protocol packet assembly, and decoding. Although machines often have efficient built-in instructions for performing arithmetic and logical operations, in fact, all these operations can be performed by combining the byte-wise operators and zero testing in various ways. For example, here is a pseudocode implementation of ancient Egyptian multiplication showing how to multiply two arbitrary integers a and b using only bit shifts and addition. Another example is a pseudocode implementation of addition, showing how to calculate a sum of two integers a and b using byte-wise operators and zero testing. As a note, in these code samples equal is the assignment operator, not the equality operator. See also. References: JTC1WG14N843C Programming Language, Section 6.5.7, Operator. Microsoft. Retrieved July 14, 2013. The Java Language Specification, Section 15.19. Shift Operators, ABJLSA Section 15.22.1, Synthesizing Arithmetic Operations Using Bit Shifting Tricks. Biscuit Key February 15, 2014. Retrieved March 8, 2014. External links. Online Bytewise Calculator supports Bytewise and OR and XOR division using bit shifts. Bytewise Operations Mod N by Enrique Zimi, Wolfram Demonstrations Project. Plots of compositions of Bytewise operations by Enrique Zimi, the Wolfram Demonstrations Project.